Okay, so what I wanted to do next here is to go over some problem-solving procedures. I listed out the key steps here for you to follow when you see this kind of questions on the homework or exam. You can always follow this uh, problem-solving procedures. So I wanted to first show you how it looks like. So in general, for this type of first order RC and RL circuits problems, what's usually involved is that you will need to have some switch somewhere in your circuit to emulate this switching event as we discussed earlier. So we need to understand first the whether the switch is closed or open at the switching instant. Okay, so that's based on the interpretation that we talked about. And then and we have to understand the circuit diagram before and after the switching event so that we can determine the um, VC at 0 minus and VC at 0 plus. Okay, and if you recall, if you look at this expression over here, right? So we have to find the final value, initial value, and the final value. And one thing that is involved over here is the initial value. Okay, so this has to be found based on the before and after the switching event. Okay, so we'll talk about that, but let me just circle back to the problem solving procedure here. So as a very first step, when you see the circuits, so you have to first identify the circuit topology before and after the switching event. Okay, so you will sketch them out. So you will have two um, circuits. Okay, and then you need to analyze those two circuits. And the second step in the circuit before the switching event, which means when t is equal to 0 minus, right? I'm assuming t0 is equal to 0. So when t is equal to 0 minus, right? That means is the time instance right before the switching event. Okay, because if I say that you know the switch is going to be closed when t is equal to 0, right? So the time instant immediately before that switching event is going to be at 0 minus. Okay, so right before the switching event, when t is equal to 0 minus, then we need to first find the voltage across that capacitor. Okay, at t equal to 0 minus. Okay, and for you to figure out the VC at 0 plus, okay, so all we have to do here, right, this is one simple step. What we have to do is recognizing that there is this thing called property of continuity, something we discussed last time, right? So we know that the voltage drop across the capacitor cannot change instantaneously. Okay, so as a result, the VC at 0 plus has to be equal to VC at 0 minus. Okay, so this tells you that once you know VC at 0 minus, then you can just equate uh, to find VC at 0 plus. Okay, and this is governed by this property of continuity. So again, voltage drop across a capacitor cannot change instantaneously. Okay, it cannot change suddenly. Okay, you can change gradually, but not instantaneously. Okay. All right. Number four, depending on whether you have another variable of interest to find or not, right? So I'm gonna just label it as y at t 0 plus or y at 0 plus. Okay. So if there is another variable that you need to find, then you will need to do the step 4. Okay. Otherwise, you will focus on step 3 and then move on to step number 5. Okay, so now let's look at the circuit after the switching event, right? So we talked about before the switching event, we found the VC at 0 minus, and then we equate that to find VC at 0 plus. But now we have to look at what happened after the switching event. Okay, so when the switch is flipped, right? And the switch is going to change its position. So now we need to use this circuit topology to find VC at infinity. Okay, so in other words, to find VC at infinity, okay, we need to look at the circuit after the switching event. Okay, for you to find VC at 0 minus, we look at the circuit before the switching event. And that makes sense because when t is equal to infinity, this is already larger than 0. Okay, so this is considered as the circuit after the switching event. Okay, so as we discussed just now, so the cap, right? So if you have a capacitor in the circuit, and when t goes to infinity, we assume that this capacitor has been sitting there for a long time. So the behavior of the circuit is going to be treated as an open. Okay, so you need to replace this cap with an open circuit so that you can find VC at infinity. Okay, so t goes to infinity. So that's what this means. Okay, VC is a function of time. So when t is equal to infinity, the cap has been sitting there for a long time. So the cap behaves like an open circuit. Okay, so step number 6 is it depends on whether you have another variable of interest that you need to find. Okay, so it depends on the question. Number 7, this is one step where you need to find your tau, right? And to find tau, we need to determine the Req, the equivalent resistance. And this equivalent resistance is basically the resistance seen or observed by this capacitor. Okay, the capacitor sees some equivalent resistance, and then you find that resistance, take that resistance, multiply by the capacitance, and then you can find your tau. Okay, so T or tau is equal to the product of R times C. Okay, Req times C. Okay, so RC time constant. And don't forget, one critical step you need to remember is you need to deactivate all the sources, okay, so that you can find the REQ. All right, and then as the very last step, all you have to do is you use this template, right? So this template is something that you wanted to remember so that you don't have to rederive the equation. So you just have to plug in your final value, initial value minus the final value, exponential function, okay, t divided by the time constant. Then you're done. Okay, so I'm going to go over a couple of examples following this procedure here. So let's go to example number 2. And example number 1, by the way, is sort of the warm-up example that we talked about. I believe it's over here. Okay, so this assumes that we already have the knowledge about the initial condition. So this is already given. Okay. All right, so let's go to example number 2. Okay. All right. So in example number 2, we have a couple of resistors. Okay, and we also have this switch involved here. Okay, so we're just going to follow the procedure here. So case 1. So case 1 corresponds to the circuit before the switching event. Okay, so before the switching event, what we need to do is we need to find VC at 0 minus. Okay, so 0 minus tells you that this is before the switching event. Okay, all right. So if we look at this switch over here, okay, if we look at this switch over here, so the way we interpret this switch is that the switch, okay, is going to go from closed to open, okay, when t is equal to 0. So that means before the switching event, the switch is in the closed position. Okay, it's only when t is equal to 0, then the switch is lifted up. Okay, so before the switching event, okay, so that's case number 1. Before the switching event, the switch is closed, right? So you see that over here, right? So right next to the 6 ohm, right? The switch is closed. Okay, so it's represented by this short over here. Okay, so this is the circuit diagram corresponding to case 1, which is before the switching event. Okay. All right, so we'll work on this one first, and then we'll move on to case number 2 for circuit after the switching event. Okay, so for the case before the switching event, we need to find VC at 0 minus. Okay, so to find VC at 0 minus, there is one assumption that we need to make over here, right? Which is before the switching event. Okay, we assume that this entire circuit, okay, has been sitting there for a long time already. Okay, so before the switching event, okay, we assume that this entire circuit has been sitting there for a long time. Okay, so we assume that the switch has been closed for a very long time. Okay, it has been sitting there for a very long time in a closed position. Okay, before the switching event, right? And it's only going to open up when t is equal to 0. All right. So if this entire circuit has been sitting there for a long time, then that means this capacitor over here. So this is the only capacitor we have, right? So this capacitor here is acting like an open, right? So again, this entire circuit has been sitting there for a long time. So this capacitor can no longer take in any more charges. Okay, so the voltage, there will be no more voltage change because the capacitor is fully charged to whatever voltage it needs to be charged to. Okay, so in that case, this capacitor behaves like an open, then the only thing that we need to do is to find the voltage drop across these two terminals. Okay, because this is my VC at 0 minus. Okay, VC at 0 minus, right, across these two points. Okay, when this cap is open. All right. So then how do we find this voltage, right? Well, so VC at 0 minus is basically the same as the voltage drop across this resistor, right? So I can combine the 4 ohm and the 12 ohm together, okay? And I can just find the voltage drop across this resistor, and that will be my VC at 0 minus. Okay. So I'll take 24 volts times 3 over the sum. Okay, times 3 over the sum. Okay. Okay, so that's pretty straightforward, right? So all we have to do is to perform a simple voltage division to find this voltage. Okay, so then we found this one, so that means we know VC at 0 minus, okay? And then the next thing we need to do here, right? So if I go back to step number 3, okay? So I need to make this claim, right? Because eventually what we're interested in is to find VC of t, okay? And for VC to find VC of t, we need to know VC at infinity and VC at 0 plus, okay? Not 0 minus, okay? 0 plus, okay? After the switching event. So what we need to do here is we need to make this statement. We need to say that VC at 0 plus is equal to VC at 0 minus. We can say this because we know VC at 0 minus from the previous step, okay? And we can say that VC at 0 plus is equal to VC at 0 minus also because of this property of continuity, okay? So this validates this statement here, okay? So we go back here. VC at 0 plus is equal to VC at 0 minus, right? Which is equal to 8 volts. And this is due to property of continuity, okay, or continuity property, right? Okay, so this is one very critical step, right? And you realize that the reason why we wanted to find this VC at 0 minus is so that we can make this claim. Okay, so that's why we have this case number 1 that we need to look at. Okay, so this is sort of an intermediate step for us to get to this VC at 0 plus. All right, so then the next step is after the switching event. So this corresponds to case 2. So for case 2, let's revisit the switch. Okay, so the switch before the switching event is in a closed position, and the switch is only open when t is equal to 0. Okay, so after the switching event, the switch is now open. Okay, so if it's now open, then my circuit diagram will only consist of this part. Okay. Only this part. Okay. So now if I just get rid of this, okay, so get rid of this part and then just focus on this, copy and paste, right? So take this entire thing, move it over to here. Okay. So this corresponds to the circuit after the switching event. Okay, so the switch is now open. Okay, so then our goal here is to find VC. Okay, is to find VC at infinity. Okay, VC at infinity. infinity. Okay, so we are going to use exactly the same trick here. Okay, so we're going to say that when t goes to infinity, okay, the capacitor has been sitting there for a long time, all right, and it's going to behave like an open circuit. So that means I'm going to replace this capacitor here, with an open. Okay, with an open. And I'm going to find the voltage drop across this open. Okay, so in other words, between this dot and this dot, right, these two terminals. And I wanted to find VC at infinity. Okay. Now, it turns out that for this particular problem, right, you can see that since there is no forcing function, no input excitation, okay, so VC at infinity is simply equal to 0, right? Because you can imagine if there is no energy source, then that means there is no voltage drop across this capacitor, okay? So in other words, there is no forced response. Okay, there's no forced response. Okay, so this is just the, coming from the question itself. Okay, so but the actual step, right, to find VC at infinity, we have to assume the cap is open, right? So just like before. Okay, so this part is still correct. Okay, but in terms of finding the VC at infinity, because there is no energy source, there is no voltage source, no current source, and so forth. Okay, and therefore you don't have any voltage drop across this open, this capacitor, okay, which is acting like an open. Okay, so then the next step, okay, is to find the REQ, right? So we need to find tau, right? But before we can find tau, we have to find REQ, okay, the equivalent resistance. So to find this equivalent resistance, we have to look at the circuit after the switching event, okay, after the switching event, okay? So we look at this circuit here. This is the circuit after the switching event. And to find this time constant, or to find this REQ first, you have to imagine you're this capacitor here, right? So now you can put back your capacitor, okay? Or you can even go back to this circuit here, right? And you imagine you're this guy standing right here, you're this capacitor, and you look all around you, right? When you look to the left, you don't see anything because now you have this switch that is disconnected from the rest of the circuit. And then now when you look up, you don't see anything. When you look down, you don't see anything. But it's only when you look to the right, right, you see 12 and 4 in parallel. Okay, 12 and 4 in parallel. Okay, so now REQ is simply equal to 12 in parallel of 4, and that will give you 3 ohm. And then the tau, therefore, is equal to RC 3 times 1/6. Okay, because C is already given to you here, 1/6. Okay, farad. Okay, and the tau, therefore, is equal to half a second. Okay, half a second. Okay, so now putting everything back to this template, VC of t. So VC of t is equal to the final value. Okay, remember the final value plus initial minus the final inside the bracket, okay, multiplied by the exponential function. And the exponential in the exponential function, you have this tau down here, right? So this is my tau, and tau, as we calculated before, right? This is half a second. Okay. So initial plus, sorry, the final plus the initial minus the final. Okay, so my final value is 0 volts. Okay, so this is my 0 volts over here. Okay. And then the initial value is 8. Okay, and I should look at this one because I need to look at VC at 0 plus. Okay, VC at 0 plus is equal to 8. Okay, this is coming from property of continuity. Okay, so I have all the variables here, okay, and just plug back into this template, and then you're done. Okay, now if I ask you to find Ix of t, all right, so where's Ix of t? So Ix of t is this current flowing through this resistor, right? So what I can do here is I can take this voltage divided by 12. okay? And then I can find Ix, right? So in other words, if I know the voltage drop here, I take that voltage divided by the resistor, simple Ohm's law, and I can find Ix out here. Okay, so now let's move on to the next example. So in this example, we have two voltage sources. Okay, so we have the 24 volts here, and then we have 30 volts here. We have this switch, okay, and we recognize that. So we have we have this hinge over here, okay, and this switch is toggling between point A and point B, okay, and we recognize that before the switching event, this switch is sitting at position A or point A. Okay. And after the switching event, the switch is going to move from point A to point B. Okay, so that's how we interpret this switch. Okay. All right. So first thing first. So case one. We look first at the circuit before the switching event. So before the switching event, I have this switch, okay, sitting at position A. So in other words, I'm only focused on this part of the circuit, consisting of 24 volt, 3K, 5K, and this capacitor. Okay, so just like what I drew over here. Okay. All right. And then, of course, the next step here is we recognize that before the switching event, the switch has been sitting, or the entire circuit has been sitting there for a long time. Okay, the switch has been closed for a long time. Okay, the entire circuit has been sitting there for a long time. So this capacitor therefore behave like an open circuit. Okay, so this capacitor is now represented by an open. Okay, and now I just need to find VC at 0 minus. Okay, and 0 minus, again, the minus sign here indicates that this is before the switching event. Okay. All right, so how do we find this VC at 0 minus? Well, simple voltage division will do. Okay, so 24 times 5K over the sum. Okay. So K, K, and K here, right, K ohm. So 5 over 8, right? Okay, so times 24, so I'll get 15 volts. And so remember, the goal here is to find VC at 0 plus, okay? Because it is the VC at 0 plus that we need in order to fill in this to fill out this template, right? So the template has a term VC at 0 plus, okay? So it's the term with 0 plus that we need, okay? So I know that because of, from the property of continuity, I can say that VC at 0 plus is simply equal to VC at 0 minus. Okay, so one is the cause and the other one is the effect. Okay, so this is again property of continuity. Okay, just to remind ourselves where this statement comes from, or where this equation comes from, right? So VC at 0 plus is equal to this VC at 0 minus, and is equal to 15 volt. Okay, so we have found one of the three variables of interest for us to complete that template. Okay, if you will. Okay. All right, so next step, let's look at after the switching event. So circuit after the switching event, this switch now is going to go from position A to position B. So my circuit is going to look like 30 volt, 4K, and 0.5 millifarad. Okay, so this is the circuit we have. Okay. All right, so then what do we do here? Well, we'll basically say the same thing here, since we need to find VC at infinity. Okay, so we need to say the circuit has been sitting there for a long time. This capacitor is going to behave like an open circuit, right? After it has been sitting there for a long time. So instead of putting a cap there, I'm just going to remove that, right? And leave it open. And since we are interested to find VC at infinity, so that is the voltage drop, at between these two dots, okay? So we need to find this VC at infinity from the circuit, okay, that we sketch after the switching event. So VC at infinity, therefore, is equal to simply 30 volts, right? I can do this by inspection because I know that there is no current passing through this open. If there is no current, so that means there is no voltage drop across this 4K ohm. So all of this 30 volts has to show up across these two terminals. Okay, so I know that VC at infinity is equal to 30 volts. Okay, so now I have collected another variable of interest. Okay, so remember we have three, right? So one is VC at infinity. Sorry, let's do the first one first. So the first one is VC at 0 plus, and the second one is VC at infinity, and then the last one is the tau, right? And before you can find the tau, you have to first find the Req, okay, and then you take the RC product to find tau. Okay, so let's find Req. Okay, so to find Req, obviously we need to look at the right circuit, right? So which one should we look at? Well, so Req has to be found based on the circuit after the switching event. Okay, so it's going to be based on this circuit over here. Okay, so then you can now imagine you're this capacitor standing right there, and then you have to find the equivalent resistance. But before then, right? So what do we do about this voltage source? Okay, well, we have to deactivate it, right? So we zero out this, we set this voltage source to 0, right? So correspondingly, that means we have a short. Okay, so this 30 volt is shorted out. Okay, so therefore this capacitor sees 4K ohm, 4K ohm. Okay, so Req is simply equal to 4K ohm. Okay, you can do this by inspection, right? Okay. At this point, we are just using very simple, analysis, voltage division, current division, okay, and then it's a simple circuit that you need to analyze, right? Then some of this can be done easily by inspection. Okay, so the capacitor sees 4K ohm. Okay, so therefore the tau is equal to Req times C, and that is 4K ohm times 0.5 millifarad, and we have 2 seconds over here. Okay. The good news is that we have now collected all three variables of interest, right? And then the next, the very last step is to go back to our template, right, and fill out this template one by one. So we have this final value, VC at infinity, and then this is VC at 0 plus, okay, not minus, but 0 plus, and then this guy here is again VC at infinity, okay, and then exponential function minus t over tau. This is my tau, right? Because tau is 2 seconds. Okay, so then that's all we need to do for this part here. Okay, or mathematically, another way of writing this is by using the step function. Okay, u of t. Okay, so now let's move on to the RL circuit. So I don't think I'm going to spend a whole lot of time on the derivation again, because the derivation is basically very, very similar to what we saw in the RC circuit. Okay, so I'll just highlight some of the key ones here. So I have so RL circuits, right? I need to have one resistor and then one inductor, right, forming some kind of RL circuits, right? But one key difference here is that for you to calculate the tau, right, it's no longer based on RC, right? Because now we change the energy storage element from C to inductor to L. Okay, so this tau is now based on, or is now calculated as L over R. Okay, L over R. Okay, so then you will carry out the KCL KVL analysis, and then you will do the integral, right? Do the integral here, and you will still end up with some natural log first, but then you will use the exponential function to get rid of the natural log, right? Just like before, right? You take the exponential function on both sides, right? So the exponential function will get rid of this natural log. Okay, so you will have the ratio here, right? So this part here moves down here. And then on the left of the left side of the equation, you have the exponential function. Okay, so you will now see that e to the minus t over tau, where tau is equal to L over R. Okay, so this is one difference, okay, between the RC and RL circuit, okay, that you need to remember. Okay, then in terms of the complete solution, the form looks very, very similar. So if you look for, and the other thing that you wanted to keep in mind here, let's go back here for a second. So in the RC circuit case, remember the variable of interest is Vc of t. Okay, is the voltage drop across the capacitor, Vc of t. Okay. Now, in the context of RL circuits, the variable of interest is IL of t. Okay, so this will be the variable of interest. It's the current, not the voltage. Okay, it's the current passing through the resistor. Okay, it's the current passing through a resistor. Okay, so and you can probably connect to this by so we know that VL is L DIL over dt. Okay, so in order for you to come up with this first order derivative, right, you're basically taking the derivative of IL, not VL, right? So then you can kind of deduce from there that IL has to be the variable of interest in order for this differential equation to be valid and therefore the solution. Okay, right. So for the complete solution, we have IL of t, and this is equal to some, right? So, this is current, right? So everything has to be in terms of current, right? So it makes sense that I have some voltage divided by some resistor here, okay? So this is my steady state response, or the steady state value, or the final value, okay, of this circuit, okay, which is based on Vs divided by R. And then the rest is your transient response, okay? Anything that is not steady state will be your transient response, okay, over here. Right, and if you look at the template here, right, it's basically the same format as the RC case, right? Because we have final value, initial value, minus the final value. Okay, and I should probably, if I want to be very specific, I'll put a plus sign over here. Okay, because it is the after the switching event that we care about. Okay, so plus, indicating, or just to be consistent with the solution for the RC case. Okay, so and then just some sanity check here, right? So this is something that you can plug in and check, right? If you plug in t equals to infinity, then you will see that eventually you only ended up with this Vs of Vs over R. Okay, so this is the current, okay, in the steady state. Okay. And similarly, when t is equal to 0, okay, so you will see when you plug in 0 here, then you will see just the initial value. Okay, by duality, right? So by duality, so if I take a step back, right, and this is something that I have been stressing several times. So if the circuit has been sitting there for a long time, right? So for an RC circuit, the capacitor is going to behave like an open. Okay, so we saw a few examples earlier. The capacitor is going to behave like an open. By duality, if I have an RL circuit, okay, if I have an RL circuit, when that after when that circuit has been sitting there for a long time, okay, then the inductor is going to behave like a short, not an open. Okay, so for example, if I have, right, so assuming I put this inductor back, okay, so after this entire circuit has been sitting there for a long time, okay, this inductor, okay, this L here, this inductor here, has been fully energized. Okay, instead of saying fully charged, right, as in the context of RC circuit, right? So we say that this inductor has been fully energized, okay, fully energized. Okay, so when this inductor has been fully energized, then that means there can no more change, okay, in the current itself. Okay, so therefore DIL over dt is equal to 0. Okay, only when this inductor is fully energized, okay, because it has been sitting there for a very long time, almost forever, right? T goes to infinity. Okay, so when DIL over dt is equal to 0, then VL is equal to 0 as well. And when VL is equal to 0, right? So where is VL? VL is over here, right? So this is the voltage drop across this inductor. So when VL is equal to 0, that means there is no voltage drop. There's no potential difference. So that means this point and this point are at the same potential, equivalent to a short circuit. Okay, so when VL is equal to 0, that means you have a short, right? There's no resistance. You have a short. Okay, so this is kind of the dual of capacitor. Okay, for capacitor, the capacitor behaves like an open after it has been sitting there for a long time. For inductor, it behaves like a short after it has been sitting there for a long time. Okay, so one is short and the other one is open. Okay, so this part here is basically the same as the RC or the RC circuit. Okay, so just to recap here, steady state and the transient response, final value plus the initial value minus the final value multiplied by the exponential function. Okay, and if you want to group it, if you want to look at it in terms of force function and natural response, right? So this is what I showed you earlier, right? Just look at the term corresponding to your input excitation. Okay, you group that together, and then this will be the term corresponding to the force function. And for the natural response, you look for the initial value or initial condition, IL at 0 plus. Okay. Okay. And lastly, exactly the same form for the template. Okay. The only thing that is different is you replace VC of T, okay, by IL of T, right? So anything that is VC, you replace it with IL, that's all. Okay. So this is for RC circuits, and this is for RL circuits. Okay. Let's go to the problem solving procedure. So by the same token, this part here is exactly the same. Okay, exactly the same, right? The only thing that is different is just the variable of interest. Okay, the rest exactly the same. Okay. Okay, so let's talk about the first example here. Well, so again, the circuit involves a switch. And the way we interpret this switch is that when T is equal to 0, the switch is going to go from closed position to open position, right? So that's when the switching happens, okay, when T is equal to 0, okay? But before then, okay, when T is equal to 0 minus, right, which corresponds to before the switching event, we assume that this entire circuit, okay, has been sitting there for a long time. Okay, this entire circuit has been sitting there for a long time. Okay. So we need to first sketch out the circuit diagram before the switching event. So before the switching event, the circuit is closed. Okay. So the circuit is closed, right? Assuming this guy is closed. So we have 40 volts, 2 ohm, 12 ohm. Okay, so I'm just following this. And then 16 ohm. Okay. And how about this guy here, right? So we have this inductor and we need to find the current passing through this inductor, okay? But we know that before the switching event, when the circuit has been sitting there for a long time, this inductor behaves like a short. Okay, it behaves like a short. Okay. So now I have to replace this inductor with a short, like this over here. Okay. And the current, okay, IL is still flowing through this short, right? But remember, before the switching event, this is this is evaluated at 0 minus. Okay, 0 minus. All right. So then what do we do, right? So we need to find IL at 0 minus, right? So that we can claim we can find IL at 0 plus using property of continuity. Okay. So then how do we go about finding this IL at 0 minus? Okay. So let's see. So if I start from here, right? So first of all, I have a short. So this short here is going to short out this 16 ohm resistor, right? So it's like if you do a parallel combination, right? This 0 times 16 divided by 16 is 0, right? Mathematically, you can do it that way, or you can simply just say, you know, this short in parallel with the resistor is going to short whatever is next to it, okay, in parallel. So this guy now is replacing the 16 ohm. Okay, so it's as if the 16 ohm is not there. Okay, and then I have this 4 ohm here between this point and ground. Okay, okay, put a ground here, some reference. All right, and then I have 12 ohm, and then I have, right, so over here, right, so I did the source transformation, ST, right? And if you recall, right, I take this voltage source, right, this voltage divided by the resistor. So I have this 20 amp, and I need to put this resistor in parallel with this current source, right? So that's how you can perform your source transformation. Okay, so that's this part. Okay, so I have 12 ohm, 4 ohm here, and so if we revisit, okay, this current again, right? So remember, this current IL at 0 minus is flowing through this short, okay? And this is the current that we need to find. But correspondingly, this current is also flowing through this 4 ohm resistor, right? So if you look at the path here, right, it's actually like this. It's going this way. So this tells us that we need to actually find the current passing through this 4 ohm resistor. If we found this current, then we know that this is the same current flowing through this inductor. Okay, then we're done. Okay, so a simple current division will do. Okay, so now basically I need combine these two resistors first, right? So that I ended up with something like this. So this is 4, and then this is IL at 0 minus, and this is 1.7, right, after the parallel combination. And this current source is 20 amp, right? So therefore, IL at 0 minus, which is, again, the current passing through this 4 ohm resistor, is simply equal to 20 times, not 4 on the top, but 1.7 on the top, divided by the sum. Okay, so 1.7 divided by the sum, right? So again, let me remind you, the current likes to travel through the path with lower resistance, okay? So to find this IL, we use the resistance on the other branch, put it on the top, okay? All right, so we ended up with 6 amp. Okay. And then due to property of continuity, we know that IL at 0 plus is also equal to 6 amp. All right. So far, so good. Next, case number 2. So for case number 2, we need to look at the circuit after the switching event. So after the switching event, let's go back to this original circuit. So after the switching event, so the switch, okay, is going to go from closed to open after the switching event. Okay, so therefore, the circuit of interest is basically this part. So I'm going to circle it over here after the switching event, right? Because after the switching event, the switch is lifted up, okay? Nothing is connected to this source, okay? So I'm just going to take this part, copy and paste. Right? So this guy here is now gone, right? So we just focus on this part. So that's what we have, okay? All right, and then so we need to find IL at infinity, right? Just like before, right? So we need to find what happened to this variable when t is equal to infinity. meaning when the circuit has been sitting there forever, what happens to my IL? Okay, the current passing through this inductor. Well, we know that this inductor is going to behave like a short uh, when the circuit has been sitting there for a long time. So this guy is now replaced by a short. So we need to find IL at infinity, which is the current passing through this short. But by the same token, right, if you recall in one of the earlier examples, there is no energy source. Okay, so if there's no energy source, then that means IL at infinity is going to be is equal to zero. Okay, so since there is no energy source, right? There's no input excitation, there's no voltage source nor current source. Okay, so therefore IL at infinity is equal to zero. Okay. Let's see. So then the next step is to find tau. Okay. So tau is equal to L over Req. Okay. And to find Req, right, we need to look at the circuit after the switching event. Okay. So we look at you can look at this circuit here after the switching event, right? And now imagine you are this guy, right? You're standing you're standing here, right? You're like this inductor, and then you look all around you, okay? And it's only when you look to the left and you see something, okay? And that something is equal to, right? It's the equivalent circuit, right? So looking to the left, you'll see some Req, and that Req is equal to 4 plus 12, right? I need to look at the one that is furthest out, okay, from the inductor, right? So the one, the further out is the 4 and the 12, right? So I combine these two first before I make it in parallel with 16. Okay, so 16 in parallel is 16. So I have 8 ohm, right? So it's this one over here. So my Req is 8, and therefore my tau is equal to L over Req. So L is, what is L? 2 Henry, right? So 2 divided by 8, so I have a quarter of a second. Okay. All right, and then remember the very last step is to, so once we have collected all those three variables of interest, then we just need to plug them back in to this template, right? So final value plus the initial minus the final times exponential function minus t over tau. This is again tau. Okay, so my final value is equal to 0. Okay, it's equal to 0. And then the initial value is 6m, right? And this 6m is found from here, from the property of continuity, right? But before you can find IL at 0 plus, you have to first find the IL at 0 minus. Okay. One more example. Okay, so in this example, um, instead of finding IL, okay, you are actually asked to find VO, okay? So VO is the voltage drop across this 2 ohm resistor. Okay, it's slightly different, um, slightly different from the previous ones, okay? So you're asked to find V naught, okay, which is the voltage drop across this 2 ohm resistor. But we still need to rely on this property of continuity so that we can find V0 at 0 plus, right? Remember, the strategy, right? So let's look at the strategy here again. So we need to find V0 of t. So to find V0 of t, I still need to find V0 at 0 plus, okay? And I still need to find V0 at infinity, and I still need to find the tau. And we know tau is, this one is very, right? So perhaps this is the lowest hanging fruit, right? So L over Req. right? L over R, right? It's something that we have done several times. And so we need to find these three variables so that we can go back and fill in our template, right, to complete this V naught of T. Okay, but for you to find V naught at 0 plus, right, we still need to rely on, or we still need to get some help from this IL at 0 minus. Okay, so that's the general strategy. Okay, so now let's look at this circuit again. So we have this switch over here, and before the switching event, the switch is closed. Okay, and after the switching event, this guy is lifted up. Okay, so now before the switching event, when T is equal to 0 minus, so I need to sketch my circuit diagram. So a circuit before the switching event is closed, so this part here is closed. So I have 18 amp, 4 ohm, 3 ohm, 2 ohm here. But now I'm going to just replace, I'm just going to do it in one step here. I'm going to replace this inductor by a short, right? And we know this because we know that when this circuit has been sitting there for a long time, this inductor is going to behave like a short circuit. Okay, so we'll simply just go ahead and replace this inductor with a short. And my current IL at 0 minus is still flowing through this short. Okay. And based on this, I need to find a way to figure out what this V0 at 0 plus is. Okay. All right. So let's do it step by step. Okay. So let's first find IL at 0 minus. So IL at 0 minus, okay. So it's this IL as over here, right? So this short here is going to short out this 3 ohm, right? Because they're in parallel. Okay. So this 3 ohm here is gone. So the circuit that I'm actually analyzing here comes down to 18 amp, 4 ohm, and 2 ohm. Plus minus still the same, okay? This part here is still shorted out, okay? And I still need to find IL at 0 minus, but that IL at 0 minus is also flowing through this 2 ohm resistor. Okay. Okay. This is my short, right? And this is the current. It's the current path. And this is IL at 0 minus that we need to find. Okay. So again, simple current division will do. So we take 18 times 4 over the sum, right, to find IL at 0 minus. So we got 12 amp. And from property of continuity, we know IL at 0 plus is the same as IL at 0 minus due to property of continuity. Okay. All right. But then this is just the IL at 0 plus, right? We're actually interested in B naught at 0 plus, right? Because we asked to find this, yeah, like this. Okay. Okay, so we go to the next step. So how do we find this guy, right? How do we find this V0 at 0 plus? Okay, so the fact that, we are looking at 0 plus, right? So we need to look at the circuit after the switching event, okay, after the switching event, okay? And you recall that this is V0, okay? And this is the voltage drop across the resistor. Okay. Some of you may be wondering, why can I not use, or why can I not first find V0 at 0 minus, okay, and then use property of continuity to equate to find V0 at 0 plus? Okay, so in other words, why don't we look at the circuit before the switching event and we find this one, and then we set it equal to V0 at 0 plus, right? But you notice that this is a voltage drop across a resistor. The continuity property does not hold, okay, for this, for voltage across a resistor, okay? The property of continuity is only valid for voltage drop across the capacitor and for current passing through an inductor. It does not hold for voltage drop across the resistor. Okay, so we cannot use this approach. Okay, and this is also illustrated in this part of the lecture notes. Okay, all right. Okay, so now, so what should we do here? Okay, so since we have already found IL at 0 plus, okay, and now we have to again make use of this property of continuity. We know from property of continuity that the current passing through an inductor cannot change instantaneously. It can change gradually, but it cannot change instantaneously. So what this is saying, okay, is that momentarily, okay, okay, IL at 0 plus and IL at 0 minus, they have to be the same, okay? And if this is true, then that means momentarily this inductor is going to hold current, okay? It's going to behave like the current source, right? It's just like in the context of a capacitor, right? If I apply property of continuity, momentarily that capacitor is going to behave like a voltage source, like a battery, which makes sense, right? But in the context of an inductor, right, this inductor momentarily is going to behave like a current source, and we are going to use this concept to move forward. Okay, so again, the goal is still to find V0 at 0 plus. So we're going to use the topology after the switching event. Okay, so now I'm going to, okay, so we'll look at this guy here. So after the switching event, remember this switch is lifted up. So we only see this part of the circuit after the switching event. Okay, so I'm going to copy this guy over. Okay, copy and paste like this over and put it here. But recall that, you know, in the circuit diagram, I'm supposed to see an inductor here, right? But now all of a sudden I have a current source, right? And this is not wrong because, you know, we just say that from the property of continuity, momentarily this inductor is going to behave like a current source. And I need to rely on this IL at 0 plus, right? And the plus sign here becomes very critical, okay? Because it indicates that this is the circuit after the switching event, Okay, so again, momentarily, this inductor, okay, is now behaving like a current source. Okay, it's now behaving like a current source. Okay. All right, so then based on this new circuit diagram, we are going to, and this arrangement, we are going to find V0 at 0 plus. Okay, so V0 at 0 plus, right? So strategically, to find this voltage drop across 2 ohm resistor, all I have to find is this I0 at 0 plus, right? So this is the current passing through this 2 ohm resistor. I take that current, multiply by 2, right? So I'm just applying Ohm's law here, I times R. So then the question is, how do I find this I, right? So, well, I can just use simple current division again, right? Because I know 4 ohm and 2 ohm, I can combine them together, right, in series. So in other words, I have, let me just maybe do it in 2 steps. So I have, this is 3. This is this current here. This is 12 amp, right? And I have these 2 resistors combined, right? So it's 4 and 2, right? So I have 6 over here. Okay. And we need to find the current passing through this 2 ohm resistor, right? This is I0 at 0 plus. Okay, but then of course the next step you can do here is you do it this way, right? Because they're all in parallel. These 3 branches are in parallel, so you're free to move them around. So you have 6 here, 3, and then 12 amp. And then you need to still find the current passing through this 2 ohm resistor. And the current passing through this 2 ohm resistor is the same as the current passing through this 6 ohm resistor, right? The current passing through this 2 ohm also passes through this 4 ohm resistor, and it's the same as passing through this 6 ohm resistor, okay, in series. All right. Okay, so 12 times 3 over the sum. Okay, the standard current division technique. Okay, times 2, right? And once I got this current, I take this current multiplied by the resistance, and then I got 8 ohm. Sorry, 8 volts. Okay, 8 volts for the voltage. Okay, but we are not done yet, right? Because this is just one of the 3 variables that we found for uh, this V naught of t, right? Let's go back to revisit our strategy here, our little plan here, game plan. So V0 of t, right, is based on these 3 variables, right? And we just tackled the first one. Okay, we'll just tackle the first one. Okay, so we still need to find 2 more, V0 at infinity and the tau. Okay, so now we can go to the second this is case 2, right, corresponding to the circuit after the switching event. Okay, so we'll redo this again. So after the switching event, so we look at this part of the circuit, copy and paste. Okay, so take this and move down here. Okay, move down here, and you realize that so and this is my inductor after it has been sitting there for a long time, right? It's now replaced by a short. So this is 3, this is 4, and this is 2, right? And this is V0. Okay, so to find V0 at infinity, right? You know, as you can see, there is no energy source. Okay, so this is kind of simplified, right? We're just trying to practice, you know, this concept over here. Okay, so for V0 at infinity, right? So this part here is more straightforward because again, there is no energy source, no forcing function, no voltage source, no current source. So V0 at infinity is simply equal to 0. Okay, so it simply simplifies the process. Okay, but then I need to find okay, so we have found this one, but then I still need to find my tau, right? So tau, to find tau, I need to find Req. So Req, again, this part becomes quite straightforward, right? Because, you know, we just need to know what is the equivalent resistance that this inductor sees. So now based on this circuit, right? So this inductor, when it looks up, right, it sees 3 ohm. When it looks down, it sees 4 and 2, right? So now what do you do there? Okay, well, so if you don't see this immediately, I have 4 and 2, which I can combine into 6. Okay, so in other words, I have this 3, this is 1 Henry, and then this is 6 ohm, right? But since they're all in parallel, okay, so I can move them around. So this is my inductor 1 Henry, this is 3, and then this is 6. So as far as this inductor sees, right, so it sees 3 and 6 in parallel. Right, so I swap the position between the 1 Henry and the 3, right? So this inductor, when it looks to the right, it sees 3 and 6 in parallel. Okay, so that's how I got 2 ohm over here for the Req. And once you know Req, and you know that this tau is equal to 1, right? Oh, sorry, inductor is equal to 1, so therefore tau is equal to L over R, so that's 1 over 2, right? So you have half a second for the tau. Right? And then the very last step, okay, we'll make use of the template, right? So the template, final value, initial minus the final, multiplied by the exponential function with this tau on the bottom. Okay, so V0 at infinity, right, is 0, okay, because there's no energy source. no energy source again over there, but this V0 at 0 plus is equal to 8. And that requires some work, right? That requires some um, some knowledge about how this inductor behaves after the switching event. Okay, and how the way this inductor behaves is that momentarily it behaves like an inductor. Sorry, it behaves like a current source. Okay, it's an inductor, but it behaves like the current source momentarily. Okay, due to the property of continuity. Okay, so the last two slides, this is FYI. So this is to kind of show you or prove to you that, remember earlier we were talking about the tau, right? And what is the tau, or what is or how many tau, okay, is needed so that I know my circuit is in steady state. Okay, it's nicely settled, right? So I gave you this little derivation here. Okay, so you can see that for when t is equal to phi tau, this y of t, okay, you can consider this y of t as your Vc of t. Okay, it's like your voltage across a capacitor or your battery, right? Charging up to 100%. Okay, so when t is equal to phi tau, you're actually charging this capacitor voltage all the way to 99.3% of the final value. Okay, y at infinity is the very is the final value when t goes to infinity, right? This is the very final value. Okay, but if you waited for phi tau, right, when t is equal to phi tau, then you're at 99.3 of the final value. So suppose if y at infinity is equal to 5 volts, right? So you can do the math, right? This is very close to phi after you multiply by 0.993. Okay, so in other words, if you look at this plot here, so phi tau, right, it will be over here. And this is very close to the final value, right? But let's say if you only waited for 1 tau, right? So let's look at the blue curve only, okay? So if you look at the blue, and if you only waited for 1 tau, right? T is equal to 1 tau, right? Then you will only be reaching, let's say, 63% of the final value, right? So 63, so you do 0.63 times 5, so you are only at 3.15 volts instead of 5 volts. Okay, so 5 volt is your final value, then you are 63% of the final value. Okay, and of course you can do this again, right? You can say, oh well, I can wait for, let's say I can afford to wait for 2 tau, okay, 3 tau, 4 tau, and so forth, right? And then you will be you'll be seeing somewhere in between, right? So between 63% and the 99.3%, right? So it all depends on how patient you are and how long you're willing to wait, right? Just like charging your phone, right? If you're in a hurry, you say, okay, I'm just gonna charge it, for let's say 20 minutes, then perhaps you only charge it to, let's say, 1 tau, or sometimes even half a tau, right? Depending on how good your charger and your battery is, right? But you would say, okay, I'm gonna leave my charger or charging overnight, right? Then eventually when you wake up the next morning, you're gonna see your phone is fully charged, right? All the way to 100%. Okay, so similarly, in the process of discharging, right, you can say the same thing, right? I can deplete my charge or my battery or voltage, okay, across a capacitor from 5 volts all the way down to 0 volt. Okay, so if you waited for phi tau over here, then you will be depleted, or you will be or your voltage will be depleted by 99.3%. Okay, so you will only end up with 0.7% over here, right, after phi tau, right? Okay.